Good day and welcome once again to our class. In today's class, we'll be proving the monotone subsequence theorem. The theorem says that every sequence has a monotone subsequence. That implies that given the sequence x sub n, then there is a subsequence of x sub n, which you can call x sub ni, that is monotone. So we start the proving. Let xn be a sequence of real numbers and set S be defined as m belonging to the set of natural numbers such that Sm is greater than or equal to xn for all n greater than m. For all n greater than m. This implies that xm is greater than or equal to every term that comes after it. That is, there exists a term xm that is greater than xn. We want to prove, or we want to show, that the sequence Sn has a monotone subsequence. We want to show that Sn has a monotone subsequence. That is, Sn has a subsequence that is either increasing or decreasing. But remember that we have said that x sub m is greater than or equal to every term that comes after it. Therefore, we can say that x sub m is a peak. And that implies that the set S, which is defined as m belonging to natural numbers such that x sub m is greater than or equal to x sub n, is the set of all the peaks of the sequence x sub n. A sequence can have finite number of peaks and infinite number of peaks. This implies that the set S can be finite or infinite. Suppose S is infinite. What does that mean? It means that it implies that the elements in set S can be what? Remember, we have said m belonging to set of natural number. So the elements can be m1, which will be less than m2, less than M3 down to Mi, M sub I plus 1, and it continues like that. And this is going to be in specific order. So this implies that the subsequence X sub Mi is a subsequence for X sub n. Now we want to show that X sub Mi is monotone. By definition, a sequence is monotone if it is either increasing or decreasing. And that implies what? For increasing, A sub n plus 1 will be greater than or equals to A sub n, or A sub n plus 1 will be less than or equal to A sub n for increasing. That implies that you want to show that X sub Mi will be greater than or equals to X sub Mi plus 1 for all I belonging to the set of natural numbers. But our set X, which we defined from the beginning, is defined as what? M belonging to the set of natural numbers such that X sub m is greater than or equal to X sub n for all n greater than or equal to m. Now this now implies that our M sub I belongs to set S. If M is equal to M sub I, then based on this definition, it implies that our X sub m is equal to X sub Mi. And in that definition of set S, X sub m is greater than or equals to X sub n. Therefore, X sub Mi will also be greater than or equals to X sub n for all n greater than Mi. But what can we say about the terms of set S? The terms of set S. You can see that M1 is less than M2, M2 is less than M3, and it continues like that. That means the terms in set S are strictly increasing. And this implies that M sub I will be less than M sub I plus 1, or that M sub I plus 1 is greater than M sub I. Therefore, since the set S works for M sub I, then it is also applicable for M sub I plus 1. X sub Mi will be greater than X sub Mi plus 1 for all Mi plus 1 greater than Mi. And that further implies that X sub Mi will be greater than X sub Mi plus 1 for all I belonging to the set of natural numbers. Therefore, X sub Mi is a monotone decreasing subsequence. Decreasing, because we said a sub n plus 1 will be less than or equal to a sub n for it to be decreasing. Suppose S is finite. Recall that every finite set will have an upper bound. This implies that the set S has an upper bound. Let U be the upper bound of set S. This implies that every term greater than U will not be in set S, does not belong to S. That is, for all m belonging to the set of natural numbers, if m is greater than U, then m does not belong to S. If m1 is greater than U, m2 greater than U, m3 greater than U, down to mi greater than U, mi plus 1 greater than U, we want to show that x sub mi is a monotone increasing subsequence. Now, if it is increasing, it means that a sub n plus 1 is greater than a sub n. Therefore, we want to show that x sub mi plus 1 will be greater than or equal to x sub mi. But mi is not in S, since mi is greater than U. Therefore, it means that what? The definition of set S is not satisfied. And what's the definition of set S? Mi belonging to S will be such that x sub mi will be greater than or equal to x sub m for all n greater than mi. In this case, x sub mi plus 1 is greater than or equal to x sub mi, and that implies that x sub mi is less than or equal to x sub mi plus 1. And our mi does not even belong to S. Therefore, x sub mi less than or equal to x sub n is true for all n greater than mi. And from this we can imply or say, let n equals to mi plus 1. And if n is equal to mi plus 1, then it implies that x sub mi is less than or equal to x sub mi plus 1 for all mi plus 1 greater than mi. But mi is greater than U. That implies that U is less than mi. Therefore, U is less than x sub mi, which is also less than what? X sub mi plus 1. And that implies that x sub m1 will be less than x sub m2, will be less than down to less than x sub mi, and that will be less than x sub mi plus 1. Therefore, the subsequence x sub mi is a monotone increasing subsequence. Increasing subsequence. And that implies that the sequence x of n has a monotone subsequence. And that is the proving of the monotone subsequence theorem. That's the proving of the monotone subsequence theorem. If you have gained anything from this proof, you can give it a thumbs up, give it a like, and share it with your friends and colleagues. Thank you. God bless you. I see you in the next video.